Yes, it's MK the guy. In this video, we are going to talk about hybridization. Here is the layout of what we are going to discuss. We are going to define hybridization. We see the procedure for hybridizing atomic orbitals. We talk about the sp3, sp and sp2 hybridization. We talk about the hybridizing sp and d orbitals. Then we talk about the hybridization of molecules containing double bonds and triple bonds, where we are going to find our sigma and pi bonds. Please don't forget to subscribe, like the videos, and share. Yes, hybridization is defined as the mixing of atomic orbitals in an atom, but this is usually the central atom. For the central atom, to generate the set of hybrid orbitals. So, for the compounds or for the atoms to make compounds, we need hybridization most times, because you find that if you just react the atoms, the geometry will be different. So let's first see the procedure for hybridizing atomic orbitals. First, we draw the Lewis structure of the molecule. Then we predict the overall arrangement of the electron pairs. These electron pairs, for the bonding and the lone pair of electrons, we predict the arrangement using the valence shell electron pair repulsion. We use this model. So this one shows the geometry. So you can know that you can use this hybridization to get this structure. Now you deduce the hybridization. Of the central. So this central atom, we said, usually it's the one we hybridize. So we do this by matching the arrangement of electron pairs with those of the hybrid orbitals. So these are the three procedures we follow. So if you put it in mind, there's no need of drawing the Lewis structure, but we are going to do that because we need to see how it flows. Let's begin with the sp3 hybridization. sp3. Here we can get some examples. For example, let's have methane, CH4. Let's first use CH4 and C. If we are to draw the Lewis structure for CH4 to be like this, then we can predict the overall arrangement for the methane. If we are to use the VSEPR model, to be like this. it will be like this. Carbon has no lone pairs of electrons. Now, so what we need to do is to hybridize carbon such that we can have this shape, because the electron configuration of carbon is 1s2, 2s2, 2p, 2p2. So meaning that at ground state we are having this. This is the first shell. Then we have the second shell like this. But let me draw like this such that we show that they are at different energy levels. At the first energy level, we have this. This is 1s2. Then at the second energy level, it is slightly above the first, but it has two orbitals. We have S, which is more closer to the nucleus, and we have also the P. But P has 3 orbitals. This subshell has 2 electrons. Here have 1, 2 in the P. So this is the ground state. Now, here we are seeing that carbon is bonding with 4 hydrogen atoms, 4 of them, meaning that we need 4 unpaired electrons, but here we have only 2, meaning that when this is the ground state. So at excited state, this electron will go to the p orbital. This orbital and the s orbital will go to the p orbital. So we shall have this. Here we have 1 electron now. This electron will be promoted to this energy level. Now we have this to this orbital. So now we have 4 unpaired electrons for carbon to bond with hydrogen. Mean that, remember, this is the shape. Now this is S, this is P, and they are slightly at different, they are in different orbitals. So for it to hybridize or to mix with the hydrogen, form bonds, they should be having the same energy levels, or they are called degenerate. So we shall have them here. You have to form degenerate orbitals. So this is the S, where it is having 2 electrons. Now these ones, they'll be at slightly the same, at the same level, at the same level. Now they are called hybrids because we have mixed this and this. So they are now hybrid orbitals. So we have this for S and 3 for P. That's why it's called sp3. We have 1 S and 3 P's. These ones will form bonds with the hydrogen. Now it's like for the S, this is the shape. And we said this is the orientation. This is the x-axis, this is the y-axis. And we have, okay, this is the z. It's like this. This is the z, this is x, this is y. So for the S, to have this orientation, and we are having 3 for the p orbital. First we have 3 of them, so we shall have D3. We say that this is -1, this is 0, this is 1. Remember, if you watch those videos about bonding, or this one can be P at X, this is Py, this is Pz. So initially we had these ones, so meaning that we had P at X, P at Y, and P at Z. So we are mixing this with this to form hybrids. So the hybrids we are forming will be in form of tetrahedral, the form tetrahedral shape. So this is this shape for the S, this is for P. Hybrids will be like this, but they will orient in this shape, meaning that we shall have carbon having this, then this, this. So this is what we are having. We have hybridized the carbon. Now hydrogen, its electron configuration is 1s1. So meaning that we are mixing the s orbital of the hydrogen with the hybrids of the carbon. So each hydrogen will form a bond, since there are 4. With this carbon. So this is the hybridization of the one of the example of the sp3 hybridization. This is for methane. Let's have another example. Another example, let's have ammonia. Its electron configuration is 2 to 5. So it is 1s2, 2s2, 2p3. So this is the first shell, this is the second shell or energy level. Meaning that at the ground state we shall have this. Shall have this. In the p orbital, we are having 3 electrons. Then this is the ground state. So someone may ask, why don't we use these electrons directly to form ammonia? Because we need 3 hydrogen. We need 3 electrons to mix with the hydrogen electrons. But if you use this one, because this is P X, this is P Y, this is P Z, they are perpendicular to each other, because this one will be at the X axis. It will be at X axis, and the other one will be at Y axis. Then this one will be at Z axis, and these lines, they are perpendicular to each other, and yet the structure we need is like this. This is the structure we need. With lone pairs. This is trigonal pyramidal. But if we just use these ones, the structure will be just at 90 degrees. Yet this one is not at 90 degrees, meaning that we need hybridization to form new hybrids. So we shall have promotion of electron from the s orbital to p orbital. Why don't we promote this electron to the d orbital? This is because nitrogen is in the period 2, and in period 2 the maximum we can have is the p orbital. We don't have d orbitals. So even if we are to promote this electron, it will go to p orbital. So it won't go to d orbital. In that we shall have this. Now this is one. Then we have this. Now the electron pair is in the p orbital. Then this and this. Then we have to mix the hybrids. Mix the hybrids. So mean that there we form the degenerate orbitals having almost the same energy level. And we need 3 electrons to form or to mix with the hydrogen. And 1 electron will remain as the lone pair of electrons. So we shall have this. This is S and we have 2p, so it is sp3 hybrids. These two will remain. They will not be hybridized. These 2 electrons. So they remain as the lone pairs of electrons. So we shall have nitrogen with the hybrids. Then these ones, they remain as lone pairs of electrons. These hybrids, they mix with the hydrogen because hydrogen is 1s. And S, this is the shape of the S electron. So this is the hybridization of ammonia. First, you have the electron configuration. If you know the structure, you do the hybridization. Then after getting you mix the hybrids. These hybrids are the one which participate in bonding. These remaining one, they remain as lone pairs of electrons. Let's have sp hybridization. For the sp, we can have an example of beryllium chloride. Beryllium, see, electron configuration is 2 to 2, meaning that we have 1s2, 2s2, 2s2. But in period 2, we have p orbitals, but here they are vacant because nothing is there. In that, at ground state, we shall have this. We shall have this. But we need to react beryllium with chloride form bonds. But here we have already double. We have 2 electrons, but we need them to be separate so that they can form bonds with chlorine. So this is the ground state. At excited state, we shall have this. 1 electron will be promoted to higher energy level. So it will go to the p orbital. To go to the p orbital. Like this. Then we have to mix the orbitals. Shall form this. So this is the sp, 1s and 1p. So we form sp hybrid or hybrids. So these vacant orbitals, they remain. So these ones are the ones which participate in bonding. And the hybrids, we say their structure is like this. So mean that we have beryllium with 2 hybrids. The hybrid electrons. Then chlorine. Chlorine, its atomic number is 17, meaning that its electron configuration, we shall have 1s2, 2s2, 2p6, 3s2, 3p5. Mean that in the outer outer shell, we're having 7 electrons. We're having 7 electrons. But if you are to draw this in the outer, we have in the 3, we have this 3s. Then in 3p, you're having 1, 2, 3, 4, 5. Mean that one electron is the one which is going to bond with these hybrid electrons, this last electron. So, and remember the shape of the p orbital, the p orbital electrons, they're like this. So, here we shall have this. So, this is bromine, this is chlorine, using its electron from the p orbital. So, this will be the hybridization of beryllium chloride. For sp2, hybridization. An example, you have boron chloride or boron trichloride. So, boron is in group 3. So, it has 3 outermost electrons. So, its electron configuration is 2, 2, 3. Now, it is 1s2, 2s2, 2p, 1. This is the outer shell or the outer energy level. So at ground state, we shall have this. With 1 electron. But we need 3 to react with fluorine. So, mean that 1 electron will be promoted to higher energy level or the p orbital. This is S, this is P. This is the ground state. At excited state, we shall have this. With 1 electron in the S orbital and 2 electrons in the p orbital. Then we form hybrids. These are sp2 hybrids, 1s and 2p's. And sp hybrids, we know its structure. This is the structure of the sp hybrid electrons. Fluorine, it is having 7 outer electrons, mean that it needs 1. And its electron configuration, it is 2 to 7. It's 2 to 7. So it is 1s2, 2s2, then 2p, 5. So if you are to draw these two, we shall have this. So we have 1 electron in the p orbital. It is alone. So this one is the one which reacts with the hybrids. So we are having 3 of them. In that boron will be this shape because it is trigonoplanar. It is trigonoplanar as we saw in the geometry video. So we shall have p electron, which is in this shape. This is the hybridization of boron trifluoride or boron fluoride. This is the fluorine and fluorine. Let's go to hybridizing sp and d orbitals. We have s, p, and d orbitals. This one, we shall have an example of sulfur hexafluoride. Sulfur hexafluoride, this sulfur is in period 3. It is a period 3 element. And these period 3 elements, they have tendency to expand their orbitals. Okay, beyond period 3, they can expand their orbitals to d orbitals. Mean that sulfur, its electron configuration, it is 2 to 8 to 6. That is its electron configuration. It will be 1s2, 2s2, 2p6, 3s, 3s2, then 3p, 4. So it will be at the ground state. This is the 1s. Then you have 2s and 2p. They are all filled. Then 3s and 3p. In 3p, we are having 4, meaning that we have only 2 which are unpaired. We have only 2, and we need 6 to react with fluorine, meaning that we need to make other 4 electrons to be unpaired. This is 1s2, this is 2s2, 2p6, 3s2, 3p4. So this is the ground state. At excited state, let's move this. We shall have one S2, then we have 2p2, we have 2p6, they are all filled. Then 3s, we have 2 electrons, 2 paired electrons, and 3p we have 2 paired electrons. But this one is promoted to higher orbital. Now, the option is to go to the d orbital. So we shall go to the d orbital. Here we shall have only 1. And these ones, they are 1, 1. For the d orbital, remember, we're having, for the d subshell, we're having 5 orbitals. We're having 5 orbitals. But we are putting only 2. So now we have made 1, 2, 3, 4, 5, 6 electrons to be paired with fluorine. Now we form the hybrids, meaning that these electrons, they are put at the same energy level. Oh, yeah, to be degenerate. We shall have all the 6. These are the S, P we are having 1, 2, 3, P3, then D, 2. In a D we are having 2. So it is sp3, D2 hybrid. Now we shall have S with O, the 6. Then fluorine forms bonds. So that will be the hybridization of the sp3. That's an example.